Hello, everybody. In this guided practice, we are going to work with the k-nearest neighbors, usually called KNN. KNN is a supervised machine learning algorithm that can classify a new item by looking at the label examples located closest to it. We will begin with a very small CSV file so that we can see the individual steps. We will calculate distance, find the nearest neighbor, and make a prediction ourselves. After that, we will use the KNN implementation provided by Scikit-learn with the IRS dataset. Finally, we will use a cross validation to help us choose an appropriate value for K. So remember, KNN predicts a class or nearby level examples. So we will begin with importing the libraries. We know that NumPy handles numerical calculation, Panda read the CSV data, Matplotlib will with Seaborn will do for visualizations. From Scikit-learn itself, we import the data dataset, the K classifier, standardization, accuracy measurement, and cross-validation tools. That's pretty much all of them through here. We also import counter from Python collection module. We will use counter when we build KNN ourselves because it helps us identify the class that appears the most often among the neighbors. If we just play around, you will see the library is imported successful because we just printed that when that get done. Cool. So let's mount our Google Drive because we just put this. I hope that you downloaded the KNN and put it there. So I already uploaded. So let's actually import my Google Drive. And I want to do something a little bit different here. I think I always do something different, right? But I want to show you best practices that we can use. We can do the remount the way that we did it last time. Or we can do something like port OS, import, actually from google.collab, import drive. That's pretty much the same thing that we've been doing over and over. Let's do a mount path. And the mount path usually is located as content drive. It will help us have something that we can do a simple validation instead of remounting. That is not that good. Let's do if OS path, and this is a not. If the path doesn't exist, and let's do our mount path. Right. If it doesn't exist, we just mount it. And let's mount our mount path. Right. And we just can print it. Let's do simple drive mounted. And we can do an else that say print drive already mounted. So if we import it the first time, it should say prime. We give the permissions. Okay, continue. Yeah, go ahead. Wait for a minute or two. And it's actually taking a lot longer again. There you go. Drive mounted, and I have that extra thing that should not be there. Cool. And we should be able to see those right here when we open the file system. Actually, it's not showing. Where is my folder? Ooh. Oop, there you go. It took a long time. Yeah, we can see the drive is actually there. Cool. And we have the files. Cool. That's what I needed. If I run this one more time, drive already mounted. We just don't need to remount it again. Yes, I think it was a really good way to show you that. Now, um, the way that we can do it is we can also check through the module that found error. That means you're running this outside. Of course, you don't need to mount it to Google Drive. That's something that is really, really important to do, right? So now that we have mounted, let's load in the CSV file from our drive itself. So let's do a simple path to get our data. And that path, let's just open it one more time. Let's do the KNN, where it says here. Cool. We remove copy path and we put that through there. Cool. Um, so now that we have that drive CSV path itself, we can do or read through pandas to visualize that. And then we can do a couple of elements there. We do require columns, missing columns. And actually, I have an extra thing here in my notes that I actually put it differently. This is a weird one, but bear with me. I'm actually doing a bunch of stuff that shouldn't. Well, let me show you exactly what I did. So, because I run it several times, it didn't work. So I uploaded, depending where you upload the file, you can have this. Let me just remove those because I don't need those. I know that it's actually there in that particular path, and we can import it like that. Cool. So now that we have, we should have some kind of validation on the column. So that's why we had it required, but we can keep as it is. You know that they are there, and let's just print those values. So we just pick the location, as I mentioned before. We can say those there, and we can set the plot at the bottom. The code checks a few possible locations. When the file is found, you just send it to pandas, right? So we'll find what contains the XYZ. The X and the Y columns are two numerical features. The C columns contain the known classes, either A or B, as we can see through here. So this is the row, this is X and Y, and A and B. So we see the data there. Now, the scatter plot gives us a visual representation of those points. The point comes from X and Y, while the color represents the known classes itself. And you can see those through the plot sizing here. Now, this small data set is useful because we can visualize, inspect the points, and understand the decision KN makes. So always inspect the data, that's really important, and confirm that the expected columns loaded correctly. So how we get the Euclidean distance? So Euclidean AB is the square root of x2 minus x1, um, and then exponent 2 plus y2 minus y1 exponent 2. So you think it's actually really, really similar to the Pythagoras theorem? It is. Now that we don't start at 0, that's why we have those values in order to get two different points through a specific plane. So we can do a simple definition function there. We send the 2 points where they are. We know that each point is an array. So we can say point 1 is a numpy array as array. And type float, and point 2 as array type 4. And we can do a quick validation if we need to. We can do through shape because they are numpy number. If the shape doesn't fit, we can raise an error, right? But let's not make it that complex for now. And let's just return the square root of the NP sum. That is pretty much this one, of 0.2 minus 0.1, elevated to 0.2. And this will do for each value of the array that they actually have here. So we can do a couple examples. Let's verify those. So let's do 4 and 1.5 with 4 and 3. And let's calculate the distance itself. Let's print it out and see what we can actually have here. Okay, so we test the function using the 0.4 and the comma 1.5 and the 0.4 and 3. So we know that the cloud distance is actually 1.5. We have the same origin. And so the difference between 3 and 1.5 is actually 1.5. It's a simple, easy way to actually see it. I hope that you are able to through that. So distance is known in KNN measures for similarity between numerical observation. That's the important part. Now let's create a simplified KNN classifier ourselves. I will print this right here. You can start reading all the elements that we have through here. So let's test those out and try to find it. So let's just do our definition, KN prediction. We set the training data and the test point, and k equal 3 in this case. So our features, into sender features and labels. In this case, our feature is training data x and y to numpy d type float. And our labels will be a column C, right? And we can just do distances, and let's do this here. That pretty much what it's doing is calculating the clear distance for every point and test point in the features that we have. So we have those there, and we can have the different name and prediction. Let me just do a couple of more elements here. And it got more imported. So nearest index, we'll see the argmaslot that give you the positions of the points from the shortest distance to the longest distance. That's what we're doing through here. So the function calculates the distance from the test point to every point in the CSV file. That's what we're doing. So let's try. In prediction function created successful. So now it means that we can start testing those. So let's do a simple testing with some values demo, and let's see how those classification actually came from. Cool. So now that we create that simplified, let's see what we can do and verify those specific ones. This same shows why k matters in the particular. When k equals to 1, single closest point belongs to class B, so the prediction is a B. When the k equals 3, two of the three closest points belongs to class A. That means the majority is changed to A in this particular case. We can see those through there, and then most of them are actually for A. With k equal to 5, class A still has the majority. That's what we can actually see through here with the X, Y, and Z. So I hope that you're able to see that. So we have 1 as B, 2 as A, 3 as 4 in the ranking specifically. And we can see the also got printed. The main point here is the choice of K can change the prediction. Now, let's visualize that neighborhood. So, and put a plot that will help us see the same classification process. So this is a long one. You can pause it. And then let me scroll down and pause it one more time. So let's just print it out and see. Cool. It's just because it has that complexity in order to see the different type of radius of how those actually work. The strong line is a radius of 1, K3 is the dotted long line, and the dashed line, and the dotted line is the K5 in this particular case. So this will help us see that classification process. Regular points are labeled training data. The X marker represents our test point. This is what we're actually testing, 1.54, 1.5. Now, each circle reaches out the K nearest neighbor, the value we tested. When the smallest circle shows the neighborhood used when K is 1, the largest circle shows the additional points considered when K equals 3 and K equals 5. The plot reinforces that increasing K expanding. So K1 predicts class B, K3 predicts class A, because that's the majority, is inside the scope, and K3 is still prints A because it detects 3 as an A and 2 as an B. So that's what I'm saying. The sizing will allow us to have it. If we have a bigger one and we pretty much cover everything, it will change to B because we have 4 different Bs and 3 different As. Here the important is it's a local voting method. K control the size of the neighborhood, and that's the important part here. Now, let's load and explore the iris dataset itself. We have the petal, we have the length, we have the width, and the sepal through there. So let's actually start seeing those. Let me load that out. Oops, I don't know how to copy and paste now. So we load the iris dataset that we had before. We do the data frame as a copy. And then we just print those out here. So we understand the basic logic. We move to a standard machine learning dataset called Iris, and we saw that before. The dataset contains 150 flowers on 3 species of Setosa, versicolor, and Virginica, I think was the name. Yeah, I don't remember well, but I think those were the actual name. Each flower had 4 measurements. For this first visualization, we use sepal length and sepal width. The target values are numerical, so we map to the species name to make the plot easier to read. And you can see that Setosa, with the sizing, is pretty much through here. Virginica is around here, and versicolor is around this other area. So we can see the sizing, yes, 150. We see different values there. Cool. So the scatter plot shows the Setosa is fairly well separated using those 2 features. But versicolor and Virginica overlap more, which means the classification between those 2 species will be more difficult to do in this scenario, especially when we are in this particular area, right? Visualization will help us understand patterns and overlap before building the actual model. So here will actually tell us where is going to be the challenge to do the correct classification that we need. So let's visualize the KN decision regions. And this actually is a really big one. We'll do the same. Oh, fit right there. So you can pause it right now. You can see the code and what it does. Let's boost it there so we can see those specific decision regions that we have. And we have those through here. So we now train the scikit-learn KN classifier using sepal length and sepal width. The model is placed inside the pipeline with standard scaler. KN is based on distance, so feature scale matters. Standard scale places the features on the comparable scales before KNN calculates distance. We will use k equal 5 for visualization. The mesh grid creates many positions across the plot. The model predicts spaces for every position, and those predictions form the background decision regions with a different color of the k to 5. So going back here, we just making those print text. Don't worry about it. You can just copy and paste, and you should be able to see that particular one the way now. Training accuracy using two features gave both 84.67. And we can see those with accurate score with the iris and the prediction one here. Now, the background shows which class KN will predict in each area. So if we choose something here, it will go to Setosa. If we have something here, it will go to versicolor. If we have something here, it will go to Virginica. Even if we have this exact one, probably it's exactly the same will be versicolor, but if we go a little bit out this point, it will actually go Virginica. So here we can have that visualization about the data and have it there where it's supposed to be. Decision regions show how those features are being separated in this particular space. So now let's choose the correct K using cross-validation. So we will use all four features for the data set now, loop through various odd case values, and record the average accuracy. And let me just copy those and put it there. We do the same that we did the first class that we saw the iris. We just got the data and the target completely. And then let's do our candidate K values in a range K divided by 3 is not equal 0. Cool. And let's do the strategic field K fold for display everything. Cool. We'll split in 10. We shuffle around a random state of 42. Then we have the mean occurrence and the standard deviation. And for every candidate, we do the pipeline for the standard scalar and K neighborhood classifier. And let's see how this actually looks like. So we selected K ourselves. In this approach is to compare several candidate values using cross-validation. So we did a different K from 1, we went all the way to 29 in this case. And we use the all four iris features for this part. Strathfield tenfold cross-validation divides the dataset into 10 sections while preserving the class proportion. The model trains on 9 sections and validates on the remaining one. This process repeats 10 times so that every section is used for validation. When average the 10 accuracy score of each value of K here. So we can see those actually have it here with the splitting size of 10. That means that we use 10 for one. And when for K in candidate K values, we just run the same over and over for every different K that's being increased. Now, the standard scaler stays inside the pipeline. This is important because scaling is fitting using only the training portion of each fold. help us avoid information leaking from the validation data. We are testing selected odd values from 1 through 29. Odd values reduces the possibility of a voting tie. We saw that before. The notebook also omits multiple of these as tie avoidance and heuristic for the three-class example, although this is not general KN requirement. The highest mean accuracy should occur at this point. We can see that the best value in the evaluation actually came in K13. So for this particular data set, we use K equal 13 to have our prediction. It has the best mean accuracy across the board, right? Let's show now the error calculation and on K. That will help us identify us out. So the lowest tested error occurs with K equal 13. So let's try to see that in our variable. So our CSV results, we put with calculation error. We do the best row, print it out, and with the best K, we do this particular line. We can see there in the plot side how those actually went through. We can see the best one was 13, but when 5, 7, 11, it's actually not that bad. It has pretty much the same mean miscalculation. Even it goes all the way to 25 in this case. So it's just to understand that. In this case, in the particular one, this doesn't also don't mean that 13 is the best one. It's the best value among the candidates that we actually test. The important lesson here is that we should evaluate K rather than selecting only for by guessing. So that is the important part. It need to be selected with the data that belongs. Now, we completed a full KNA workflow. We loaded CSV. We created the Ludian distance. We did all those here on the top. Then, without the value of K changed prediction because it changed how many neighbors participate in the vote. And it was here. We then apply scikit-learn KN classifier for the IRIS dataset. And without that through here. And then I made to remember that the K predicts from nearby levels of observations. Distance is central to the algorithm, so feature scaling can matter. Small values of K can be sensitive to individual points, while large values smooth the decision too much. Finally, cross-validation helps us select a value of K is more likely to perform well on new data. So far, I hope that you like what we actually saw today. Meanwhile, if you have any question or any doubt, you probably have, please don't hesitate to reach me. Happy coding, everybody.